Okay, 3.4, graphing functions. It's a very important section because it gives you some freedom in how you graph some of these functions. It's very important to distinguish the difference between discrete and continuous. And so that can lead to some confusion, but overall it's a very simple concept, very intuitive overall. Once you get the hang of it, you'll get the hang of it. So beginning with this first problem, we have a function. Now this function here is not in a graphable format. A function that we would like to have is where we have f of x equals or y equals. Essentially where I can just plug in to my x and I can get my output of y. But if I plug in something for x here, I'm not going to get y as my answer because I have to plug something in for y as well. And that's not very helpful. So what we're going to do is we're going to rearrange this function into a format where the y is all by itself. You can see kind of that process sort of already being worked out here, but we'll show you all the steps. But once the y is by itself, then I'll be able to plug in my x number and just evaluate and get my input and my output. Rather straightforward. So how do we do that? And then when we graph it, we'll graph it on this domain. Now this domain is discrete rather than continuous because it's telling us to use only the points at 0, 3, 6, and 9. And that is all. So when we graph this function, we're only going to do it at those 4 spots. But let's get back to rearranging this function, right? Our goal is to have the y by itself. Now let me zoom in on this. So you'll notice that the y is on the left side of that equal sign. And so that's where we want to isolate it. We want the y to be the only thing on the left side of that equal sign. So in order to get this y by itself, I'm going to have to find the way to get rid of that 3 and to get rid of that x. If those two things can go away, then the y will be by itself. General rule of thumb to remember is the piece that's attached to the y that we're trying to get by itself, we'll save for last. So since the 3 is attached to the y, it's a part of that term, we will save that for last. And we'll just start by moving this x term out of the way. Let's get rid of this x here first. So now, in order to get rid of it, we have to find a way of canceling it out. So since I have a regular 1x, I can turn it into 0 if I subtract 1x, right? X minus x becomes 0x, and therefore nothing, right? And therefore it cancels out. So by subtracting x, I'll be able to cancel it out. But to keep the equation balanced, we have to subtract x on the other side of the equal sign as well. So what we end up with is the x's disappear. The x minus x is 0, so it's gone. But on the right-hand side, we're going to have 15 minus x, which you can write like this, but I'm going to write it the other way around, where I like to have the x term first. It'll come in handy later on. So I'm going to write this as negative x plus 15. Okay, it's still a negative x because the x has to have the minus sign because it's a minus x. And the 15 started as a positive, so it has to remain a positive, which is why I wrote it as plus 15. Okay, you wouldn't want to write it as x minus 15 because that's wrong, right? Then you're making the x positive when it shouldn't be, and you're making the 15 a negative when it clearly shouldn't be. So negative x plus 15 it is. So I've gotten rid of that x, and now I have to worry about getting rid of that 3. Now it's a little different here. We're not going to subtract 3 because 3y minus 3 doesn't cancel the 3 out, doesn't cancel anything out. What we're going to do is because it's being multiplied with y, that 3 is being multiplied with y, we're going to divide by 3. And here's the reason why. Look at what happens technically, right? When you do 3 divided by 3, what do you get? You don't get 0 because we don't want 0y here, right? 3 divided by 3 turns into 1. That 3 turns into a 1y because 3 divided by 3 is 1. So it's 1y or just plain y, which is what we wanted, right? We just wanted y by itself. We didn't want 3y there. We wanted 1y there. So dividing by 3 does that for us. So we have to divide the other side by 3 as well. So we'll have negative x divided by 3, and we're going to have 15 divided by 3. And this simplifies to just negative x divided by 3 plus 5. Now you're going to notice that the function that they use, they've written negative 1/3 x. Keep in mind that negative 1/3 x is the exact same thing as negative x over 3. I'm going to prefer this rather than the negative 1/3. But in case you're wondering, it's the same thing because it is technically a negative x is technically a negative 1x divided by 3. And negative 1 times x is the same thing as negative 1/3 times x. So they are equivalent, but I'm going to just use the this version of it because it's a little easier to evaluate when I plug things in. So now what we're doing is we have our domain 0, 3, 6, 9. So these are, again, the input values. These are the x values. So we're going to plug them into our function, and we're going to see what output we get. So you can see that here are those x values, those domain values 0, 3, 6, 9, and here's us plugging them in. So when you plug 0 in to the first one, again, I like to think of it as -0 divided by 3 because it's more like that. I get 0 plus 5, which makes the output of 5. So when you plug in 0, you get an output of 5. Now let's plug in 3. When you plug in 3, again, I'm going to consider it more of -3 divided by 3 rather than like this. Remember, these are the same thing. -3 divided by 3 is -1. So this becomes -1 plus 5. -1 plus 5 is 4. So that's why the output there is 4. So we plugged in 3 and we get out 4. If you plug in 6, -6 divided by 3, again, this is the same thing as this. I'm just writing it over here because this makes more sense. -6 divided by 3 is -2. So this whole thing is -2, and -2 plus 5 is +3. So we got an output of 3. And then when you plug in 9, -9 divided by 3 is -3. -3 plus 5 is 2. So when you plug in 9, you get an output of 2. So now you have the points that go on your graph. You've got 0, 5, which will go, let me zoom in. 0, 5 will go right here because notice these are going by 2. We got 2, 4, 6, 8. So 5 is going to be right in the middle. 0, 5. 3, 4 is going to go right here. 6, 3 is going to go there. And 9, 2 goes here. And we are not going to connect this with a line because it is discrete. We are told only to graph those 4 points at 0, 3, 6, and 9. I've graphed those 4 points, and now I'm done. I am not going to draw a line here because it is not continuous. Okay, so that answers these questions here. Number 1, why do you not connect the points? Problem was discrete. Okay, domain was discrete. Now, how would you graph it differently if the domain was 0 to 9? This would say that it's continuous. It would be continuous. We would draw a line. Okay. So now let's talk about where we're really going with this. Okay, so if the domain of a function is all real numbers, any number can be used as an input value. So this one's already worked out for you, but let me kind of talk you through what the plan of action is for each of these problems. So we're going to be given a function like y equals x squared. And now this function exists on all x values. So that means the domain is all real numbers. It goes from -infinity to +infinity. So technically, we can pick any number we want as input numbers. We can pick -20. We can pick 3,000. We can pick any number to input and find an output for it. Now, however, what we're going to try and do is we're going to try and pick a few input values, a few numbers for x, plug them in to get output values. Because when we pick x values to plug in, we'll make an ordered pair, and we can graph that ordered pair. And what we want is we want to plot enough points to be able to see what the shape of the graph looks like. And once we know what the shape of the graph looks like, then we can connect the points with a line. Okay. But the problem is, well, it's not really a problem. It's actually more of a good thing for us is we can pick any numbers we want to plug in, any numbers at all. However, although you can plug in any number you want, you're kind of limited to the space on your graph. So if you pick a number that's not going to be able to, if you have a point that can't fit on your graph because your graph is too small, well, then you can't really use that point because it won't fit on your graph. So you can see in this example, they have selected these numbers, -3, -2, -1, so on, because those numbers give you output values, give you points that can fit on your graph. So -3, 9, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, and 3, 9. Those all fit on that graph. And so we were able to plot those points notice that the pattern was a U shape, and then connect those dots with that line. Connect it with that U-shaped line. So that's the approach. We can pick any numbers we want to plug in. We're going to collect points. We're going to create some points. We're going to plot them on the graph until we see what the graph looks like. Once we know what the graph looks like, we'll draw our line through it and make it complete. Okay. So for this example, they've already done the fun part for us, which is they've already picked x values again. They've already decided to plug in -1, 0, 1, 2, 3, and 4, and that's fine. We're going to do that. We'll get kind of a slow start to this, but we'll be all right. So our function is 3x minus 5. So they've selected to plug in -1, and when they plug in -1, 3 times -1 minus 5 makes -8. So they would have the point -1, -8. They've selected to plug in 0, and when you plug in 0, you're going to have 3 times 0 minus 5, which is -5. So you plug in 0, you get -5. There's another ordered pair. There's another point that we'll graph. When they plug in 1, they get the answer of -2. So when you plug in 1, you get a result of -2. When you plug in 2, you get 3 times 2, which is 6. 6 minus 5 is 1. So when you plug in 2, you get an output of 1. When you plug in 3, you get 3 times 3, which makes 9. 9 minus 5 makes 4. So when you plug in 3, you get an output of 4. And then when you plug in 4, you get an output of 3 times 4, which is 12. 12 minus 5 is 7. You get an output of 7. So they've picked these numbers to plug in, and they've gotten their output values, so they created all these ordered pairs. So now that we're going to plot these ordered pairs and see what our graph looks like. So -1, -8. It's going to be right here. 0, -5. 1, -2. 2, 1. 3, 4, and 4, 7. So we've plotted those points, and now we get an idea that our graph looks like a line. It doesn't really have any curve to it. Our graph is a line. So now that we know the shape of the graph, we can connect all these points with a line to sort of complete the whole thing. So there you go. And put arrows at the end. It's very important that we put arrows on the end because we only graphed a few points, and this graph does continue past the border of our graph. It does continue forever. So it's important that we put arrows in there at the end to indicate that it does keep going. So the points appear to form a line. So we draw a line to kind of complete the whole graph, and then draw arrows at the end as well to indicate that it continues to go on forever. Now, when graphing a function, does it matter if it's written in function notation? The answer is no. So whether it's f of x or y equals, f of x equals or y equals, outputs will still be the same. So you're going to have the same ordered pairs no matter what. Whether it's written f of x equals or y equals doesn't really matter because you're still just getting the same exact points and you're still plotting the exact same points. So when it comes to graphing, it really won't make a difference. Okay, so now let's graph this function. So let's do this all completely on our own. Here's how we would do it on our homework. Here's how we would do it on a quiz or anything like that. So we have a function y equals -x squared. So what we're going to do is we're going to pick x values to plug in. We're going to just pick any one that we want, but let's try to pick one that will fit on this graph. Obviously, it wouldn't make sense to try and pick 50 because 50 won't fit on the graph. But let's pick some numbers that will fit on the graph, and then we'll see what the output is, and we'll plot those points. Now, a good rule to follow is, and you can tell from this example up here, is it's really nice if we pick some mixture of negative and positive numbers. Because, for example, if we, on this graph, only plotted positive numbers, right, only plotted at 0, 1, 2, and 3, we did not plot any of the negatives, we would have thought that the line would look like this, that it would probably continue going this way. But by plotting the negatives, we can see that the line actually goes back up, right? So it's important that we get a little bit of both sides because you never know. If we only plot the positives, we wouldn't know that it would go back up on this side, right? For all we know, it probably could continue going this way or something like that. So it's important to kind of get a full shape. getting a few positives and a few negatives. Okay, so let's start. Let's try picking -4, right? Let's pick -4 and let's just see where that gets us. Now, when I plug it in, I have negative and then -4 squared. Now, keep in mind that these negatives here don't cancel each other out. A negative, negative. Why is that? Because when you follow the order of operations, PEMDAS, you actually do exponents before you do multiplying. So you're not going to multiply these numbers together. Remember, think of this like a -1 times a -4 squared. You can't multiply those together because you have to deal with the exponent first. So really what you're doing is -4 squared first. -4 squared is -4 times -4, which is positive 16. So really we have a -1 times 16, right? Because we had to do this first. And then that negative now gets attached to that 16, making it a final result of -16. So this is equal to -16. Now you'll notice when I try to graph that, -4, -16 is too far down here. I won't be able to fit it on my graph. So we're going to throw this out. That's not a very good input value to use. Let's try instead, let's try -3. Let's see if that works better for us. So when I plug in -3, same idea, right? -3 squared is positive 9, and then positive 9 times that negative will make it a -9. And that point fits. -3, -9 fits on our graph. So now that we're on a roll, let's keep going. -2. If I plug -2 in, I have positive 4, -2 squared makes positive 4, times a negative, which makes a -4. So -2, -4. If I plug -1 in, -1 squared is positive 1, but positive 1 times a negative makes a -1. And if I plug in 0, I have -0 squared, which is still just 0. So I get the point of 0, 0. All right, so I got a few negatives. Let's plot a few positives as well. So if I plot positive 1, I'll have 1 squared, which is 1. But remember, you got to attach that negative to it at the end. So it's going to actually be -1. As a result, when I plug in 2, same thing will happen. 2 squared is 4, but the negative makes a -4. And when I plug in 3, -3 squared is 9. So it'll be -9. So I have 3, -9. So I can see what my graph looks like. It's got that arch shape. It's got that upside down U shape to it. So now that I know what it looks like, I'm going to draw my line connecting all the points and with my arrows at the end. So remember, you're picking these numbers, okay? You can choose whatever numbers you want. But generally, it's helpful if you pick some negatives and some positives. And if you pick any numbers that you can't fit on the graph, then just throw that out and pick something else, okay? So I have another function here, y equals -4 x 2. So again, we're going to pick some values for x. We're going to plug them in. We're going to see what we get for y. So let's try -4 again, right? If I plug -4 in, we'll have -4 times -4 plus 2. Now this creates a positive 16 plus 2, and a positive 16 plus 2 is 18. And again, I can't fit that on the graph. So this isn't going to work. Let's try -2, right? Let's plug -2 in. So -4 times -2 plus 2, that's going to be positive 8 plus 2, which is 10. And that one does fit. It barely fits, but it does fit. -2, 10 is way up here. So now that we're on a roll, let's keep it going. -4 times -1, we'll plug this in. This becomes 6, so we'll have that point at 6. -1, 6 is here. Then we have 0. If we plug in 0, we're going to have the answer of 2. So we'll have 0, 2. Oops, it's going to be right there. Plug in 1. -4 times 1 is -4. -4 plus 2 is -2. So that'll be 1, -2. If we plug in 2, -4 times 2 is -8. -8 plus 2 is -6. And can I fit 3 in? Plug in 3. -4 times 3 is -12. -12 plus 2 is -10. So yeah, that one barely fits. All right, so I've got all the points I can really fit on this graph. So now that I see that the shape is a line, I'm going to connect these all with a line. And hopefully your line looks straighter than mine. And then we can draw the arrows at the end. So hopefully yours is a straight line. Mine should be a straight line. All right, we're going to skip this next page because it talks about graphing calculators, and we're not going to deal with graphing calculators. But we're going to move on to the word problem. We'll finish with this word problem here. So now when it comes to word problems, right, the domain is very important because the domain has to be reasonable. All right. So for example, I said let's use some negatives and positives, but why would we use negatives if we're talking about time or distance or things like that, right? Some things can only be positive. Time, distance, number of people, you wouldn't have negative values for those. So when you're choosing to plug in numbers, you're going to see in this example, they're choosing positive numbers because it doesn't make sense to plug in any negative numbers because it's a word problem, right? It's you're not going to have to deal with negative time or things like that. So only use numbers that are reasonable for your word problem. So in this word problem, it says the Mid-Atlantic Ridge separates the North and South American plates from the Eurasian and African plates. The function y equals 2.5x relates the number of centimeters y the Mid-Atlantic Ridge spreads after x years. Graph the function and use the graph to estimate how many centimeters the Mid-Atlantic Ridge spreads in 4.5 years. So our function, which is y equals, oops, let me zoom in here. Y, I think I got it. All right, there it goes. All right, took a second. Y equals, okay, no, it's lagging now. All right, so what I'm going to do is instead of writing it, I'm going to just scroll down here and I'll show you the textbook. They've all got it worked out for you. So I'll just talk you through what they're doing because my pen's not working properly right now. All right, so the textbook, here they go. So the function y equals 2.5x describes how many centimeters the Mid-Atlantic Ridge spreads after x years. Only use non-negative values of x and y. Use a graph to find the value of y when x is 4.5. Okay. So what they're doing is they're choosing numbers that make sense in the context of this problem. So they're plugging in numbers like 0, 2, 4, and 5 because it doesn't make sense to plug in a negative number of years, right? So they plug in 0 to find out how far it's gone after 0 years. They plug in 2 to find out how far it's gone after 2 years. They plugged in 4 and they plugged in 5 to find out how far it's gone after 4 and 5 years. So when they plug those numbers in, at 0, they get the answer of 0. So they plotted the point 0, 0. At 2, when they plug 2 in, 2.5 times 2 is 5. So they get the output of 5. 2 years is 5 centimeters. So they plot that point. They plugged in 4. 2.5 times 4 makes 10. So 4 years, it's 10 centimeters. And they plugged in 5. 2.5 times 5 is 12.5. So they have the point 5, 12.5. And now those points are enough to kind of get an idea that your graph looks like a line. So they connect those points with the line. And now they're using that information to figure out, answer the question where the question asks, how many centimeters will go in 4.5 years? So they have a little dotted line. You'll see that coming out of 4.5. They have a dotted line going up to the graph, and it looks like it hits right at about 11, right? Depending on how straight your line is, it's right about 11. So it's about 11. They say 11.25. But yeah, it's right about 11 would be our estimate, would be our guess. So the distance the Mid-Atlantic Ridge spread increases as the number of years increases. So the graph is reasonable. We can see it going up. When x is between 4 and 5, y is between 10 and 12.5, right? When we graphed 4, we knew it was at 10. When we graphed 5, we knew it was at 12.5. So when I graph 4.5, which is right in between those, then I'm expecting my answer to be right in between 10 and 12.5. So our guess of about 11 makes sense because 11 is between 10 and 12.5. And that's how you'll do these word problems. So you'll have to pick values of x yourself, just like you did with regular functions, and graph it. But only pick values of x that make sense in your domain, something that's reasonable, okay? And I'm going to end the video there. I think that concludes what most we're going to say. I'll see you guys in the next one. Bye.